Swayam Prabha. Digital India. Educated India.
We have been analyzing the two-dimensional motion of bodies, and essentially the bodies are two-dimensional in nature, in the sense that in the third direction they don't have any variation. It's the same thing which has been pulled out. Okay, another example here. Last time we have seen the rectangular plate is swinging about two axes, which is just swinging in a curvilinear translation, and then there that was a simple motion. The constraints were very simple since it was a translation. It didn't have any angular motion. Angular rotations were absent, and then the point G again was quite simple. It was going through a circular motion, and so has only tangential and normal acceleration. Okay, so that was simple. And then another very popular example in this dynamics 2D motion is a rod here, like a ladder, which is put against a vertical wall resting on the ground here at an angle of theta. Okay, and its length is AB, L, and then it has a mass M. So as usual, as you understand here, when this starts sliding, the point A moves on the horizontal ground, starts slipping, and even the B starts moving on the vertical wall, along the vertical wall, it slides, and then its motion is vertical. And as you can see, as we have explained a number of times, so this is a general plane motion, not a pure translation, and so it has all the components of G as well as rotation. Okay, so now let us see. Our interest is to find out what will be the accelerations of G. G is here, and the angular motion. Or on the other hand, if your interest is only in theta double dot, so that also is of measure. So now let's look at how we can apply the dynamic equations. For that, let's draw the free body diagram of. In fact, now you can recall the importance of the free body diagrams, which we started off in the static equilibrium case. We should completely understand when you free the body from its surroundings. So we show it as a diagram here, together with its interactions with the neighboring bodies to which it was in contact. So what is their effect? In particular, we want to show the internal forces as external forces on this one. So we have AB here, and being acted upon by weight at its center, and its angle here is theta. Apart from this, so since it's sliding on the ground here, so we have normal reaction, and in the vertical direction here, and from the vertical wall here, we have normal reaction at B. So that's in the horizontal direction. And this will give rise to and we make it equivalent. So it will so essentially it can be made equivalent. It has linear accelerations here in the horizontal and vertical acceleration. So if you want to make this equivalent to this one, we will multiply with m here, and together with this we also have Ig times alpha, right? Okay, so this is Ig times alpha. So you can see now here we are going to get three equilibrium equations. So the three equations are summation of all the forces in x direction is this is the x equation, and this is the y equation, and moment about g. Okay, so these are the three equations, and how many unknowns are there here? If you count the unknowns here, we have the reactions Na and Nb. Okay, and what else? And three acceleration components. Okay, so we have five unknowns and three equations here. So that means that we have to get three more equations from the constraint motion. So what is the constraint? The constraint is that point A is supposed to move on the horizontal ground and B is moving with the vertical wall. So it's moving against the vertical wall. So these are the two constraints, and let us see how we can put those things. So the constraints are kinematic constraints, or the which the kinematic constraints are point A is constrained to move on horizontal ground. So which means that acceleration of A is x component is there, so but its y component is 0. And so similarly point B on vertical wall, so which means that the B x component is 0. So these are the two constraint equations. Okay, so we have to get these things. So these are not given at G, but these are given at A and B. So that means that if you want to get relationship between AGX and AGY, so we have to relate A and G. So like this. So acceleration of A is acceleration of G, and A with G. And right now I can write acceleration of A with respect to G will have two components, a normal component and a tangential component. Okay, so AG is AGX. Let us say I can write I J, and A with G is A and G are at a distance of L by 2 omega square, and it's directed along B to A, right? Directed along B to A. So we can say like this, and then L by 2 times alpha, and here we can write it L by 2 times, or if you want it everything in terms of A, I and J, we can also do that. It's minus Poisson vector of A with, this is how we can write it, Poisson vector of A with G, and then alpha K cross. So this is a very general formula. This is the tangential component, alpha K is the angular acceleration, K is the Z axis, and A with J. So if you take the cross product, so that's what you get is tangential component. So let's expand this one, and omega square or A with G, I'm sorry, we are, yeah, A with G is how much? So this is A and G here. So A with G is L by 2, L by 2, so this theta here. So x component is L by 2 sine theta, right? I and minus L by 2 cos theta J. So this is as far as this is concerned, plus alpha K cross, same thing. Okay, so let's simplify this one. Let's collect I components, Ajx, and then this is omega square L by 2 sine theta I Aj y and minus omega square plus omega square L by 2 . And also we have another component here which has to be accounted here. So if you go and take I, so that is J, K cross J will be minus I, so that will be plus. We have to add that also here. And then here also we add K cross I is J. Okay, so this is acceleration of A. So the constraint here is that, what is the constraint? So constraint here acceleration of A in the y direction is 0, right? So, or its jth component is 0, which means that this has to be 0. So, this is the jth component, right? So, and further that since it is starting from rest, okay, so this also we use omega is 0. So, what essentially we have here AJY plus L by 2 alpha sin theta, or L by 2 sin theta. So, this is acceleration of g in the y direction is minus L by 2 alpha sin theta, right. So, similarly we can also apply using a acceleration of b in the x direction is 0. So, we get L by 2 alpha cos theta. So, what we have done is that by doing this, so we have imposed two conditions on the motion of g, so that the acceleration of A is completely in the horizontal direction, there is no vertical component, and then here we used that point B is having only vertical motion, there is no horizontal motion. So, using that we have this. Okay. So, using this, now we simplify the diagram as follows. We are drawing it again here. All right. So, now the things have been, so this is AGX is L by 2 cos alpha. So, it's minus, M L by 2 alpha cos theta, and then AGY, the y component is negative. So, we put it like this. Okay. And then we also have alpha here. Okay. So, now you can see that the number of unknowns now have reduced to 3 only, Na, Nb and alpha. Everything else, so that AGX, AGY now are written in terms of alpha, right. So, using this now you can formulate the three equations. So, the three equations of dynamics equation. So, Na is M L by 2 alpha cos theta, right? So NB minus W is ML by 2 alpha sin theta, and moments about the point here. So Na times L by 2 sin theta minus NB times L by 2 cos theta, and W does not have anything. So this is equal to Ig times alpha. Ig is 1/12 ml square. So these are the three equations, and then you can solve for the alpha here, right? Okay. So of course you can solve, okay, the three equations. For example, here you can substitute Na and Nb here, and then you can solve for alpha. Substitute Na is small mistake here. This is Na. Yeah. Okay. So this is how you have to solve for the unknown. So I think I'll leave that at that point. But however, if you're interested in alpha only, so we can avoid Na and Nb by taking the moments about center. We take so if you take the moments about C, then it's only W L by 2, and this is L by 2, and this distance is L by 2 sin theta. So this is just equal to what is that which we have to get? We get the moments of all these things here. Okay. So for that we have Ig alpha and M L by 2 alpha cos theta times L by 2 cos theta plus ML by 2 alpha sin theta by 2 sin theta. So this is how it is. So you can take alpha out. L by 2 square alpha cos square theta sin square theta and then so this is 1/12 ml square, this is 1/4 ml square. So this is just equal to 1/3. So from this you can take L and L, you can cancel, and you can cancel G 3/2 L sine theta. So it's very important for you. Not only you just blindly apply the theory, but it's also important that you apply or modify those equations so that you can get the equations in a simple manner, so that you can evaluate the quantities of your interest quickly and easily. Okay, so this is about this problem. Just on the another simplification here, we have obtained this the constraints. We have obtained the constraints applying the equations on A, for example, that its acceleration in the vertical direction is 0, its acceleration about B is. So for that, so we can also get this one much easily if you apply the graphical diagram. So the constraints by graphical approach. This is also important. So what do we mean by this? So we relate A and B. So for example, the acceleration of B here is acceleration of A, B with A, two components, the normal and component. Okay, so what we know here, this is the graphical approach. Acceleration of B is only in the vertical direction, acceleration A is in the horizontal direction, and this is L square omega, and then this is B to A in this direction, this is L alpha in this direction. Okay, so the directions have been shown here, right? So in fact, whether this is in this direction or in the upward direction, we do not know. So this can be drawn. This is acceleration of A, and to which this is 0, omega is 0. And so that means that if you draw a line here of acceleration of B with respect to A, the tangential component, which is L times alpha here, like this one. So you should end just below O in the vertical direction, so which is acceleration of B. Okay, so this is the graphical representation of the acceleration diagram. So this is the acceleration diagram. Okay, so why we have drawn this one is that this is acceleration of A and this is the representation of B in the acceleration diagram, this being origin. Okay, so to locate G here, we can also get the image of the point G here quite easily by looking at points A and B. So in the physical coordinate system, AB are like this and this is G, right? So we have proved it earlier that in the acceleration image also they will have the same proportionality. So if G is the center point of A and B in the physical plane, so here also G will be in the image of acceleration in the acceleration diagram. So G will be in the center of AB. Okay. So if G is the center, so that means that if you draw from an arrowed line from O to G, so that is acceleration of G. Okay. So this is what we learned. So we can use this knowledge by writing AG. Okay. So for that, so if acceleration of A is like this, if this is the angle theta, so we know that if this is L alpha, AA can be written is nothing but L alpha cos theta and AB is L alpha sin theta, right? And acceleration of G then, so it is nothing but half of AA, so it is L alpha cos theta by 2 in the downward direction like this, and this L alpha sin theta by 2 in the downward direction. Okay. So in fact, this is what you have got by applying AA in the vertical direction is 0, AA in the horizontal direction for B is 0, AB, and that is what has been applied here. And from that we deduced what will be G, and the G will be only in terms of alpha. So this is L alpha, we know that, and from that we got A and AB, and half of it will be acceleration G. So this is what you can directly get as a constraint equation. So this is always it's always convenient if you can draw the acceleration diagram and get the constraint equation. Okay. And apart from that, once you have this, the rest of the procedure is applying the dynamic equation. So now let's look at another interesting problem. A connected body. So in this, what we use is a block here, okay. So the lengths are so this is block A, and the force F is applied on the block, and this is block A has a mass, and rod B has rod let's say log 1. Okay, and so a force F is applied on A suddenly, and this is at an angle of theta naught to start with. So our task is to find accelerations of the system immediately after starting. As soon as it starts, so you are supposed to find out the acceleration. So if you look at this one, this is connected bodies A and B. So A is resting on the horizontal ground and AB is an angle of theta naught to start with, and it has a mass of m2. So it has a, obviously it has a weight here. So now to analyze this one, so there is a connection here. This is not a rigid connection, and then it is a pin. So there is a freedom of this swinging about this point A. So now let us draw the free body diagram. So the free body diagrams are, so this is block A, and then there's a normal reaction here, and there's a weight, the block, right? And that's the free body diagram. And what else? So if you draw the free body diagram of the rod also, the rod is acted upon by weight, and what else? There are other things here, force. So there's a pin connection here. So obviously you have there are internal forces Fx and Fy without any moment. Okay, and obviously these two internal forces should also be shown here, and they are as external forces Fy, Fx and Fy, right? So these are all the forces acting on block A and block the rod AB, right? And then what is this now? This is the actual forces which are acting. So they will create accelerations, motion, and okay, so it's mass times acceleration. Okay, so already we are using the constraint here that it's moving only in the horizontal direction. And here this we show Gx Gy Okay, so these are the complete free body diagram of the two bodies, right? So if you look at the number of unknowns to be solved, what is that? N here, fx, y, and acceleration of a and agx, agy, and alpha. Okay, there are 7 unknowns in the number. And how many equations do we have here? So there are 3 here, and what about here? What about the top one? The top one is how many equations do we get? Do we get 3 equations for the top one? So top one will give us only 2 equations. Why? Because the top block we assume it to be a point mass. So point masses will have accelerations ax and ay, but there are no rotation. So this will give us 3 equations here, and this will give us how many equations? Only 2, right? So because this is a point mass. Since this is a point mass, so we'll have 2 equations, and this will have 3, and totally we get about 5 equations, and we have 7 unknowns. So that means that we require 2 more equations, right? 2 more equations. So what is that which we can get? So we have to put the constraint here. Constraints are that point A has, of course, a horizontal motion only, obviously, right? It has obviously, so that's what we are using anyway. And what else? We also have the rod is rotating about A, so that means that this G is related to A. Okay, so what we mean by that is that this AA here and the G are not completely independent, so there is a certain amount of relation, right? So A and G are related. Yeah, so what we are saying here is that there are 2 bodies here, and then what we get is 5 equations. So this is 2 equations because the point mass. So we have only sigma fx is 0, sigma f, I'm sorry, not sigma fx is ma, and sigma fy is may. So that way you will get 2 equations. And then this being a rigid body, so you will get 3 equations, totally 5. But however, we have 7 unknowns. This is n fx fy, aa, agx, agy. So the other 2 equations which we need here comes from the constraint. So what is the constraint? Constraint is that these 2 bodies here are not disjointed. Looks like here there is disjointed free body diagram, but there is a connection here. A point A is common to both of them. So that is where the accelerations, whatever the velocities are all same for both the bodies. So the kinematic constraint here, kinematic is geometric motion. The kinematic constraint here is point A is common, open for both the bodies. So which means that G can be had acceleration of g can be related to acceleration of a. So what does that mean? So what we mean by that is that and further, of course, acceleration of a is only horizontal. So that also is there. And let's just see what we have here is that so acceleration of a here is related to acceleration of g by a with g. This is the general relationship. So this is normal and this is tangential, and normal is depends upon omega. So we have a ai a gxi a gyj. This is for g and this is 0, and this is what we have here for k cross a with g. So a with g is L by 2 sin theta I and L by 2 cos theta j. Okay. So if so, then what we have, let's, or we can even directly write it by, let's write the relationship for I. So we have AA on this side, we have dx here, and then we need an I here. So k cross j is I. So that is alpha times L by 2 cos theta alpha. And so similarly we have for j, we have 0 is a gy plus alpha times by 2 sin theta. This is k cross I is j. So thus we have a g. So we require a g here is nothing but a plus a by cos theta times alpha, and a gy is L by 2 times alpha sin theta. Okay, so these are two additional equations which we got. So this is in addition to our 3 plus 2 equilibrium equation, right? Coming back here, so what we write here is that instead of agx here, we'll replace it by aa plus L by 2 cos theta times alpha. Here we replace by gy with a minus sign, L by 2 alpha sin theta, and then this is alpha. Okay, so now if you count the number of unknowns here, so there are 2 less here. The unknowns are here n, fx, fy, and a, and here the alpha. So now two nodes have been reduced and we have 5 unknowns. Okay. The dynamic equations, so equations are so let's write it. So it is here minus fx plus f MEA. Okay. So finally, again, we are summarizing all the equations and n, the y equation is n minus y minus w. That's the y component is 0 here. So this is for the block A point mass, and then here we have again. So here for the second body, for the rod, this is for A. The rod. So we have here fx, the x component of the equation is fx only. So that's equal to m times. On the right side, it is AA L by 2 alpha cos theta, right? And y component is Fy minus W for this one. We can say W2 here is M AG. AGY is L by 2 alpha sin theta, and moment about the point G here. This is moment about G here. So that's Fy L by 2 sin theta. So this is theta, and then this is L by 2 Fy. Okay. And Fx minus, okay, L by 2 cos theta, and this is equal to. Okay, so this is how you can formulate the equations. Okay, and then these are the 5 equations. In fact, as you go on doing that, in fact, fx and fy, from here you can take fx and fy, substitute it here, and then and here and here. So you will have the equations in n and alpha and A. Okay, so you can take these 3 equations. So once you put down, giving a long expressions for this equation is difficult. So if you put down some numbers, so you should be able to solve. Okay, so this is how you can solve. You can solve, substitute fx and fy. I'll just write it here for the sake of completeness. From 1 and 2 in 3, 4, 5, and solve for n, A, and alpha. Okay. So that I'll leave it as an exercise. So now that everything is clear, so from 7 equations, right now finally we came down to 3 equations which are not difficult to solve. And by the by, so I also have to tell, usually the formulation of these equilibrium equations is not that difficult. but only the constraints sometimes are difficult to imagine, as well as sometimes it's difficult to frame those equations. So let's also, just like we have seen in the other problem, let's also see if there is a shortcut, if there is a shortcut for constraint. So print simplified version of the constraint in graphical form. So I urge you to practice this graphical formulation of the equation, so that two things. One is that you will get an idea, you will get a physical idea of what's really happening. The other one is, on many occasions this will turn out to be simpler. For example, we want to get AG related to AA, as well as we want to find out what is the acceleration of G, point G. So if you look at point G, so we have A here, so we have acceleration of A like this, and if you want to get the acceleration of G, so we can write G as acceleration of A and G with A. I'll write only the tangential component, normal component which depends upon omega square, so that is usually 0. So here we want to write AG. So we'll know that acceleration of A is horizontal, so we'll represent it by an arrow, and G with A. So assuming that alpha is like this, so that means that alpha is counterclockwise. So what we have here, so together with G, so it is the acceleration of G with respect to A is nothing but, we are assuming that A is stationary and we are looking at the acceleration of G with given alpha as angular acceleration. So that means that this is nothing but L by 2 times alpha at an angle of theta. So if this is theta, and we'll write it as L by 2 times alpha. This is how you can represent it in a graphical form. Total acceleration of G is acceleration of A plus this much. So that means that graphically you can say that acceleration of G here is acceleration of A plus acceleration of Z here. So the effect of these are not really the components. So these are not components. So this is a summation. So if this is summation, so that means that this point G is having an acceleration of A as well as a plus L by 2 times alpha. So this is how you can write. So just to put it in a, what we will have, sum it up finally. So this approach, by this approach, by this graphical approach, so what we have here, again we have to write these things. In the graphical approach, it essentially changes this part only. So when we write equivalently, so what we have to write here is this. So this is how we write. So this is how we write again in a graphical manner by simplifying the depiction of the acceleration of g here. So now you can see here very nicely. So this gives you two equations, this gives you two equations. There are only 5 unknowns, fx, fy, n, a, and here there is only alpha. That's all. So you can write down these equations. Now the whole problem is simplified to this one, and you can solve here. I mean, of course, you will get the same answer, but then if you do this way, you will have not only you will get a lot of idea, you can picturize the whole problem, but the equations also get simplified. Okay, I hope we have done some 3 problems of increasing complexity. One for the first one we took as a pure translation. The second one is a rod which is in general motion, and the third problem which we have taken is a connected bodies. So many combinations are possible, but essentially what you have to keep in mind is that you have to look for how many bodies are there, how many equations are coming. Each gives you sometimes 2, sometimes 3, depending upon whether it's a point mass or a rigid body. And then anytime 2 bodies are connected, then it will have some constraints. So you have to put those constraints also together. So please look before you actually embark upon the solution. Please look at whether the number of equations and the number of unknowns are matching. Then only you go ahead. Otherwise, something is not right and something is missing. Okay, I think I'll stop it here for this analysis of dynamics of 2-dimensional bodies. And next, this is using the force acceleration approach. And the next topic is we'll talk about impulse momentum concept of the body. Okay, we'll stop. Bye.